Hello everyone, thank you for attending the presentation for work on legalization of die bonding bumps and pads for 3D ICs. This presentation is arranged as follows. We start by introducing the problem of 3D routing, and then we do a quick analysis of the exact problem that we are facing, which is the legalization of 3D vias and the persistence of the problem across different technology nodes. We propose different solutions for solving this problem, and then we analyze the performance of these in the result section. In a traditional 3D IC, the pitch of a 3D via, uh, uh, the 3D via is basically the via which is connecting the tiers as shown here. It's determined by the pitch value that we use, and this pitch value can vary quite a lot depending on the connection. For example, a monolith 3D via has a size that is comparable to any other 2D vias, and a hybrid bond pad, on the other hand, usually has a via pitch that is much larger than any 2D routing widths. Acro- Usually, it's about 1 to 10 micron for the hybrid bond pitch, uh, which makes them significantly large and creates problems during 3D routing. In current 3D IC flows such as Pin 3D and Macro 3D, the routing here is done all at once. So basically, all the 3D routing is done in a single stage using commercial EDI routers. The benefit with such an approach is that the router can provide a good routing solution based on the congestion and timing criticality of the design. But as we see, this can be a problem when it's used on a 3D design if the pitch is quite large, which is usually the most common case. In 2D EDA tools, routing is done in two stages, like a global routing stage and a detailed routing stage. Usually, in the global routing stage, the VRs are not taken into account for like congestion and other calculations. So it doesn't consider the VR sizes because it assumes that VR size and the metal sizes are similar. But when if you use the same router for a 3D where the VR is quite large, it creates issues uh, that that can't be seen in global routing, but once during detail routing, when it adds the 3D via, the huge size of the via causes issues. In both here, as we can see, like in both memory on logic with macro 3D and logic on logic with pin 3D, as we increase the 3D pitch size from the smallest size, for example, memory on logic, it's done with the hybrid bonding. So as we go from 1 micron to 10 micron pitch, the number of overlaps between the vias increase quite a bit. And then similarly for the pin 3D, here pin 3D is done with the monolithic 3D flow. So the pitch sizes are quite small with 0.1 micron to 1 micron. And even in its range, when we go to the higher end of its range, we see there is a lot of overlaps between the via. We see the layouts of an application processor designed in 28 nanometer technology node. The via pitch of a 3D connection is varied from 1 micron to 10 micron. And for reference, the 2D technology node we used here has an M6 pitch of zero point 0.1 micron, and the via connection to the metal layer also has a similar pitch. The layout snapshots show 3D vias, which are highlighted based on the uh, overlap. If the VI is blue, it means that the VI location is legal. There are no overlaps. A red means that the VI is overlapping with one or more other VIs nearby. And here, as we see that the overlap becomes more and more severe as the pitch increases. And this impacts the timing and design QR because this has to be resolved during detailed routing stage by moving the VRs more and more further than the initial global routing solution, and which will not be an ideal case. Similar to the increase in VIA pitch, the issue of the VIA overlap also worsens when the technology node is advanced. With advanced technology nodes, the backend of the line dimensions are shrunk, and the 3D VIA pitch is now relatively larger as it's not scaled based on the 2D process. The 3D VIA pitch depends on the 3D technology that we use, such as like hybrid bonding and monolithic 3D, and not the 2D tech nodes. The table here compares the dimensions between the 28 nanometer and 16 nanometer nodes. Here we see that the G cell, which is the global routing grid used in the global routing stage, the G cell also reduces in size significantly from the 16 to the 16 nanometer node. As a result, the overlap issue worsens. To show this, the layouts are split into bins of 25 by 25 micron size. At most, a bin of this size can fit 25 vias of the 5 micron pitch, but as we can see in the 16 nanometer node, there are a number of bins that have more vias than the capacity of the bin. Note that like even in a bin without any overflow, like if a bin has less than 25 vias, it doesn't mean that they're strictly legal because there can be a large density of vias where like 4 or 5 vias can be pretty close to each other, overlapping, and there they can be the only vias in that 25 by 25 bin. Then there won't be any overflow, but there are still overlaps. But it means that these overlaps can be removed within the same bin itself, and they won't be quite severe as we don't need to move outside the bin. Uh, the 3D VR density is depends on like the router, like how it when we use the router to do the whole routing, it depends on like where the router wants to place the VRs, and also based on the pin density or the pin connections, 3D pin connections between the two tiers. So it can be quite easily controlled during routing. In general, the 3D flow comprises of 3D floor plan placement, clock tree design, full 3D routing, and post-route optimization, especially for macro 3D. Here in our proposed solution, what we do is that the routing is modified as a multi-stage process. First, the 3D nets are routed using a traditional router, and this would have the same problems as before. But then we introduce a VIA legalization step to remove all the VIA legalization issues. So this has the advantage of using the routing solution from EDA, which has a good 3D, a good routing engine. But in order to remove the overlaps, we try to use that initial solution and just modify the solution via locations a little bit so that we are not losing the strength of the 3D of the EDA routers. And then once this is done, a complete routing, incremental routing is done for the 3D nets to finish the routing without any violations. And then we do the routing of the entire chip uh, for the non 3D nets. For the legalization, we use two algorithms. First one is a bipartite matching based legalizer, and the second one is a force based legalizer, which is more traditional. In order to use a bipartite matching legalizer, VIA legalization problem is first transformed to a matching problem. Consider a layout with 3D VIAs, here they are shown in red. Uh, these VIAs can actually be illegal VIAs with overlaps with each other. So first we construct a grid, and this grid, the width and length of the grid is the x and y dimensions of the 3D VIA pitch. So the grid locations, intersection locations, which are shown in blue, uh, are legal VIA locations. So if we place VIAs along across the grid intersection, there won't be any overlaps. We first create one a bipartite matching where each VIA is matched to all the legal locations, and the cost of each matching is basically the distance between each via and a legal location. So here, because we will always have like fewer number of vias than the number of legal locations, we are going to add a lot of dummy vias so that we can form a complete bipartite matching. So from this bipartite matching, we create the weight matrix, uh, and then using the weight matrix, we give this as an input to the linear assignment solver, and this would basically give us the output for output which minimizes the overall cost of the solution, and so we'll get a optimal VI assignment solution. The linear assignment problem is solved using the uh, shortest augmenting path algorithm, but the problem here is that this algorithm can have quite a high time and space complexity, especially because we have a lot of legal grid points in any given layout, and so we we introduce a divide and conquer approach by splitting the whole floor plan into different tiles, where each tile can be considered as a single unit, and multiple of these tiles start to form a window, and this window is slide across the whole floor plan, and within each window then we solve the optimization via assignment problem optimally. And in order to minimize the local optimality, we try to maintain overlap between two adjacent windows so that the solution in one window is going to impact the solution in the adjacent window. The parameters for the tile, window, and stride uh, are varied in the predefined range. And within this range, we find the optimal parameters based on the time taken and the solution quality using a Bayesian optimization. So the parameters are tuned using the machine learning optimization, and then this helps us to strike a good balance between local optimality and overall time taken. The next solution that we propose here is a more traditional force-based solver. In this method, forces are added on a pair of vias when they are overlapping with each other, and then the vias are moved along the direction of the resultant force. And not just not just a repulsive force, an attractive force is also added that pulls the via to their initial location, so that any vias that are moved too far away can be tried to pull back slowly without adding any new violations. Additionally, clock vias can be modeled to have a larger mass, so they do not move hugely from the initial solution that is defined uh, by the router. And similarly, we can add the cost or the weight of the vias based on the timing. Uh, and then the force is also modified as the number of iterations progresses. So initially, uh, the force is quite large in the immediate neighborhood of the vias. So the immediate neighborhood will have a higher impact initially, but then the force of the vias that are farther are then become stronger and stronger as the iteration progresses, so that we can try to get a good solution overall. This is the overall modified routing flow in a pictorial form just for the 3D nets. So we first route 3D nets, and then there might be overlaps between any two vias. First, we remove all the other shapes apart from the via 3D vias, and then using these via locations, we using either like the bipartite matching or the force based legalizer, we legalize these vias, and then once we then fix these vias and then incrementally route the 3D nets, so that the router is going to use the vias that are already present in the design. And quickly comparing the placement results, what we see here is that first with no via legalization, and then the second one is with force-based legalization, and finally as with the is the bipartite matching legalization. The design that we use here is an application processor implemented in a 28 nanometer technology node using a 5 micron 3D hybrid bonding via. The 3D design is of a memory of logic is of memory of logic type, where memory macros uh, that are corresponding to L2 cache are placed on one tier, and all the other cells are placed on the top. The 3D connections made to these are made to these memory macro pins, and usually and because memory macros have pins on a single edge, that's why we see a high concentration of the pins in these straight lines, which are basically the edges of the memory macros that we place. Force-based legalization basically pushes these vias away from these hotspots, but we see that there are still some hotspots in the middle that the force-based legalization is still not able to completely fix as the number of iterations increase. And since we limit time threshold, it's not able to completely legalize the whole design. Uh, in matching the bipartite matching based legalization, what we clearly see an underlying grid, which is the grid that we use in order to find the legalized via locations, and all the vias are snapped to these grid locations. And here we see it's actually much more tighter than the force based solution. It's because the force based solution is just a heuristic, whereas the bipartite matching, we use a well-defined algorithm, which is the shortest path augmenting algorithm, to find a one-to-one to find a mapping from the via points, via locations to the legal grid points, and we consider all the grid points which are located like here in this case like 5 micron from each other, as opposed to force-based legalization. And when we look at the results of the PPA results from looking at the following table shows the results of via legalization methods in terms of design QR. The default design has almost 5,000 vias, and of this 5,000 vias, there are almost 3,500 violations, which is quite a lot. But once we use either like force-based or bipartite-based legalization, all the violations disappear. We also see there's a decrease in the via count, and this is because we first do the 3D net routing, and we limit the vias only on 3D nets, and we don't use any 3D vias for any other 2D nets, or basically there's a stricter use of the 3D vias in these two methods because of the modified 3D routing flow. That's why the number of vias decrease, and because of the legalization method, the number of violations decrease, and because because of this, like because once the 3D vias are routed, and then the 2D routing, global and detailed routing can be done as usual without any disruptions from the 3D nets. The worst net is like improves slightly, but total net is like improves quite a bit compared to the default method. For Microbump 3D design, we only use bipartite matching based assignment as the VIA location needs to be aligned to a predefined manufacturing grid in a Microbump 3D. So force based option cannot be used to satisfy this requirement, and will limit our legalization options to just bipartite. Here, the VIAs are pre-assigned to a legal grid location, and the assignment is correct by construction for a Microbump 3D. So there wouldn't be any overlaps between the bumps right from the construction stage. When compared to a naive way of assigning the bumps using a greedy process, bipartite matching based assignment shows much improved QOR in terms of the worst native slack, total native slack, and the wire length. This shows the robustness of the bipartite method as it's applicable for both uh, hybrid based bonding and microbump 3D. Finally, monolithic 3D is the most advanced form of 3D bonding, usually with a via pitch that starts at around zero point 0.1 micron. The violation problem doesn't occur at such small via pitch until we reach around 1 micron. Additionally, monolithic 3D has such a large bandwidth, 3D bandwidth, and this allows for a highly interconnected 3D designs as seen from the 50,000 vias or 58,000 vias in these designs. Due to this large number of vias, the two dies are tightly connected to each other, and using a simple legalization based overlap remover does not work its best, and we still see a few overlaps remaining in the design after our legalization stage. As we see, initially it starts at around 5,000 violations, but even after legalization, even though the violations are almost one tenth of before, they are still present. And the impact of legalizing vias on such a highly interconnected design is that the total native slack has a significant impact compared to other designs, as well as the violence is noticeable increase with our legalization. Even though like the maximum displacement and the average displacement are pretty small at like max displacement at only just 6 micron or 4.5 micron with bipartite, and average displacement almost at half micron in each stage. Even such a small displacements are able to create a significant difference in the QOR. In conclusion, we showed how a realistic 3D pitch value can cause various routing issues in different types of 3D ICs. We proposed a modified routing solution with two different uh, legalization solutions for the VRs, and we still make use of the EDI routing for improved timing and routability. The solutions, especially bipartite matching, is applicable over a wide range of design types and pitch values for 3D ICs, and shows improvement to routability and the timing of the designs. In advanced cases such as monolithic 3D IC, this warrants a complete change to the routing solution in order to tackle the problem of via overlaps when there's a high 3D connectivity. Thank you.